Okay, here we are, 8-5, day 1. And what we're going to be looking at today is finding volumes of objects created by revolving an equation. So in the last section, we just found the area between curves by doing the areas of the rectangles. We did the height times the width, top minus bottom, or left or right minus left. What we're going to do today, and I'll do the best I can at drawing this. We're going to suppose we have the equation y equals x to the 1/3, and we're going to look at it with the domain restriction from 0 to 8. And then we're going to take this equation and revolve it around the x-axis. Okay, if we take a look at that. Okay, y equals x to the 1/3 kind of takes off and opens up like this. And we're only going to look at the chunk that goes from 0 to 8. Let's just say this is 8. And then what we're going to do, so we'll take that point, pretend that's gone. We're going to take this equation and revolve it, right? Think three-dimensional, come all the way around, off the paper, up and around, and behind the x-axis. So I'll do my best at drawing that. So it kind of has a round opening here. Well, not round, kind of oval. And then you can imagine the bottom part of it here. So you could think of it as a kind of like a vase that comes down to a point, like half a football even. And what we want to do is find out the volume of this space that we created when we revolved it. And what we're going to do is take our little rectangles in here, and each rectangle, as it revolves around, if you can see the shape that it's going to create, grab another one here. Take that rectangle, spin it around, you're going to get little discs. And the discs are shaped like cylinders. Or you can think of them as like coins. They're supposed to be a little more round than that, but that's the best I can do there. We're going to be finding the volumes of those little cylinder pieces, and then we'll use the integration technique to sum them all up all the way through. Let's see if I can get a picture in the book, in case you didn't follow that. You can see it right here. So here was the kind of like the shape that I started with, and they take this rectangle, they revolve it around, and you can see the little gray disc in here. Each of these discs is the shape of a cylinder on its side. So what we're going to do is, when we integrate, we're going to write the equation for the volume of a cylinder, and then integrate on our boundaries. So the slices, so the volume is the sum of the volumes of the discs, which are cylinders. And remember, the volume of a cylinder is pi r squared h. So if you take a look back at our cylinder, the radius is determined by the height of our rectangle. So there's our radius. That's our r value. So our r is our height, and our height is determined by our equation, like top minus bottom. And the height of our cylinder, the little skinny cylinders laying on their side, the height in this case would be our dx. So the radius is your function value, and your height is your dx. So our volume equation then is the integral from a to b That's our left x boundary to our right x boundary of pi r squared h. And when we substitute in, they will be our x values, boundaries, pi. To get our radius, that's the function, because we're going around an axis, remember that equation is 0, so it's just the function minus 0, so it's just the function. We'll have to square it, because that function is the radius, and the formula says you got to square the radius, and the height is dx. So let's use this first one as our first example and find the volume of that half a football there. So our boundaries I gave you from 0 to 8. The volume of the cylinder is the pi. Pi that is always going to be there. The radius is determined by our equation, x to the 1/3. And I've got to square that. And our height is dx. Okay, before I integrate, I think I'd like to multiply this, because it's a power to a power. You multiply exponents. So 0 to 8 pi, that'll be x to the 2/3. And then now we're ready to integrate. And it's just a power. Remember, pi is a constant. You could pull that out in front if you wanted to, just to get it out of your way, but you don't have to. I just kind of imagine it going out to the front and not being in my way. So I carry it along. Add 1 to this. Add 3, that'd be 5/3 times by 3/5. And then evaluate from 0 to 8. And then it's just typing this into your y equals if you want. Well, you could just type it in once with an 8 in there. Oh, I don't have the answers. Dang. I don't have a calculator handy either. Well, I'll run and grab a calculator real quick because I'm going to need it later on. So give me 10 seconds. Okay. So clear that stuff out. Got pi, 3/5 pi, 3 pi divided by 5 times x raised to the 5/3. 8. Oh, anyway. So 60.32 minus 0. Cubic units. Okay, not too difficult. Let's turn things around. Now let's revolve around the y-axis and see what changes. Alright, so let's say, okay, let's take that same equation and revolve it, stop there at 8, and revolve it around the y-axis. So now we're going to spin it this way and then behind. So you will get something that kind of looks like this. So it's that funnel. Oh, that one went a little high there. Oh, close enough. I wish I'd kept this down a little bit. There. All right, so now we got to slice them this way. That means our rectangles have to be in here like this. And then as we spin those around, we get our cylinder shapes coming out like this and back behind there. Okay, not good at all, but again, our cylinders are going to be laying parallel to the x-axis. So now it's still a cylinder. The volume is still pi r squared h, and our radius is determined by the equation. Our height is this thickness, but that's a dy now. And our boundaries need to be on the y-axis. So, to set it up for volume, we want y values here. Pi. The function needs to be in terms of y this time. So it's f of y squared. So you want to see y's in here. And then the height of each cylinder is a dy. So notice, if you're going around the y-axis, you need y boundaries, the equation solved in terms of y, and a dy on the end. For the other one we just got done doing, everything was in terms of x boundaries, a dx, and the function in terms of x. So it's very important that you draw the little rectangle in. So here we go again. Example 2. Find the volume of the region bounded by, find the volume of the region in the first quadrant bounded by y equals 1 minus x squared and rotated about the y-axis. Okay, sketch is huge. Start with a sketch. So if I graph 1 minus x squared, and I only want the part that's in the first quadrant, so from there to there. Oops. So I'm taking this and rotating it around the y-axis. Okay, so right away, I need my rectangle to go around the y-axis, so I need my rectangle to be perpendicular to the y-axis like that, so I can spin it around and create those cylinders that are laying flat and stacked up. So I know I've got a dy. What I need is, I see 0 here. I need this upper y boundary. So if I find that first, I know that this point here, I know the x is 0 because it's just on the y-axis. So if I put 0 in here for x, the y is coming out 1. So I know my upper boundary is at 1. So when I set up my integral, I'm integrating from 0 to 1. I want pi r squared h. The h is this distance here. It's a dy. I've got the pi. What I need is my radius, but in terms of y.